Okay, let's jump right into this. Welcome to The Explainer. Today, we're unpacking a concept that is quite literally the hidden heartbeat of the universe. It's an incredibly elegant mathematical rhythm known as simple harmonic motion. And honestly, once you see it, you can't unsee it.
So, think about this for a second. What could possibly connect a massive skyscraper swaying in the wind, a tiny, invisible atom vibrating in a crystal, and the steady, rhythmic swing of an old grandfather clock? Seriously, on the surface, they seem completely unrelated, right? Different scales, different materials, different purposes. But under the hood, they are all dancing to the exact same mathematical beat.
And that beat is simple harmonic motion, or SHM. Now, the absolute key to understanding this is something called the restoring force. SHM is a type of periodic motion, meaning it repeats at a very predictable rate. But here's the kicker. The farther you push an object away from its resting point, its equilibrium, the harder it pushes back. It's basically a never-ending physical tug-of-war.
So here is our roadmap for today. We'll start with the rhythm of nature, then dive into the math and energy behind it. Next, we'll uncover a really cool connection to circular motion, look at what happens when things fade out with damped oscillations, and finally, how to keep that motion alive using forced resonance.
Starting off with Section 1, the rhythm of nature.
Well, let's look at the classic examples physicists use to model this. A mass on a spring and a simple pendulum. They both show harmonic motion, but they get there in totally different ways. For a bouncing spring, the time it takes to complete one cycle, its period, only cares about two things: the mass of the object and how stiff the spring is. But a pendulum? Totally different beast. Its swing is completely independent of the mass you hang on it. Instead, it relies entirely on its length and the constant pull of gravity. And there is a really fascinating quirk here. Because gravity pulls straight down, not perfectly along the curved path of the swing, the restoring force is actually a pretty complex trigonometric function. So strictly speaking, it's only considered true simple harmonic motion when it's swinging in very small angles, just a tiny bit away from the center.
Moving right along to Section 2, the math and energy.
So what makes this back and forth so perfectly harmonic? Well, if you track an oscillating object over time, you don't get some chaotic random squiggle. You get these gorgeous, perfectly undulating sine and cosine waves. Position, velocity, and acceleration are all intimately linked here, but they're totally out of phase. Think about it. When the mass is pulled to its absolute furthest point, it actually stops moving for a split second. Velocity is 0. But right at that exact moment, its acceleration is maxed out, pulling it violently back toward the center.
In those waves, they perfectly mirror what's going on with the energy. Don't think of kinetic energy, the moving stuff, and potential energy, the stored stuff, as just isolated numbers. Think of them as partners locked in this continuous dance. At extreme displacement, all the energy is stored as potential energy. But as it snaps back toward the middle, that potential energy plummets to 0, and it's entirely replaced by kinetic energy as the object whips through the center at top speed. They just keep trading places.
You can really see it with a pendulum. At the highest points on the left and right, kinetic energy is 0 and gravitational potential energy is totally maxed out. Then, right in the middle, it flips. Kinetic is maximum, potential is 0. And if you add them together to get the total mechanical energy, it stays perfectly constant. Well, assuming there's no friction to steal it away, of course. It is just this beautiful closed loop of energy, swapping back and forth. Which brings us to Section 3, the circular motion connection.
Okay, this is one of my absolute favorite ways to visualize those abstract sine waves because it reveals the hidden geometry of the whole system. Picture a vertical disk with a wooden peg on the edge, spinning around at a perfectly constant speed. Now shine a light straight down from above so the peg casts a shadow on the floor. As the disk spins in a circle, what's the shadow doing? It's not moving in a circle, it's just moving back and forth in a straight line along the floor. If you plotted the shadow's position over time, you'd draw the exact same graph as a mass bouncing on a spring. It's a literal shadow. One-dimensional simple harmonic motion is just the shadow of two-dimensional uniform circular motion. How wild is that?
Let's move on to Section 4, fading out damped oscillations.
Now, as elegant as that math is, it is mostly theoretical. Because we live in the messy, friction-filled real world. And out here, things eventually stop moving. A spring just won't bounce forever. All physical systems deal with damping forces that bleed away mechanical energy, usually turning into heat. Imagine a mass on a spring, dunked into a thick fluid like oil. As the mass moves, the fluid pushes back. And this damping force,
whether it's fluid viscosity, internal friction, or just air resistance, is typically proportional to velocity. So the faster the mass moves, the harder the fluid resists. Ultimately, that causes the amplitude and the energy to just decay over time.
And that decay can take a few different forms. With light damping, or underdamping, the system still oscillates, but it gradually fades out, kind of like the lingering sound of a struck tuning fork. But then you have something called critical damping. This is where the damping force is tuned so perfectly that the object snaps back to its resting position in the absolute shortest time possible, without bouncing back and forth even once. Engineers use this on purpose all the time. It's literally how the shock absorbers in your car keep you from bouncing down the highway every time you hit a pothole.
And finally, Section 5, staying alive with forced resonance. So if damping is always trying to kill the vibe and stop the motion, how do we keep things moving? We fight back by adding a driving force. This is driven harmonic motion. The secret here is timing. You have to apply that external force in perfect sync with the object's natural frequency. Think of a grandfather clock. It has a mechanism that gives the pendulum a tiny, perfectly timed little nudge on every single swing, just enough to make up for the energy lost to air resistance. Or even simpler, pushing a kid on a swing. You don't just shove them randomly, right? You push exactly at the peak of their backswing. That perfectly timed force causes the amplitude to grow. That's resonance. And it's everywhere. It's a pendulum making another pendulum swing through sympathetic vibration. It's even the secret behind those soaring, endless notes on an electric guitar, where the amplified feedback acts as a driving force to just keep the string vibrating indefinitely.
So, as you can see, simple harmonic motion is way more than just textbook math. It really is the heartbeat of the physical world. From vibrating atoms to skyscrapers swaying in the breeze, literally everything has a natural frequency waiting to be activated. So I'll leave you with this. Take a look around the room you're in right now. The chair you're sitting on, the desk, the floorboards. What hidden resonant frequencies are surrounding you right this very second, just waiting for the perfect driving force to bring them to life?